Hey everybody, thanks for clicking on this video. So this is a question that I've been asked before, and it's taken me a little while to sort of work things out. And it's a question I've wanted to answer for a long time, just things get busy and all that. But I finally got around to work out an answer to this question. Now, in researching this, I have to admit that this is something that if you go to Gizmodo.com, they did write an answer. They claim that the Death Star cost $15.6 septillion, and this was published in 2009. So you're asking, okay, why are you doing this video? Well, I'm going to answer this question a little differently than what they did here. And that's because what they did is they focused mostly on materials. Talk about metal, talk about air, talk about shipping, and that's about it. I'm going to take a little bit more of a different approach when it comes to answering this question. So here's the approach I'm going to think about. In order to answer this question, I'm not going to say, all right, let's just make up a Death Star. No, let's try and answer this with what we have right now in the real world. So the first question that we need to answer is, what is a Death Star like? What is something we already have right here, right now, that's kind of similar to a Death Star? Now, if people think about that, maybe their first thought may be something like the space shuttle. Well, goes into space, right? Well, the space shuttle is kind of designed for something different than what the Death Star is designed for. The Death Star is designed to blow up planets. The space shuttle is designed to go into space and then land again, and then go into space and land again. It's designed to be reusable. The Death Star, obviously being so big, never has to land on a planet. And so for the way it's built, has a lot of aerodynamic qualities, the space shuttle does, that the Death Star doesn't. And so that's why I'm going to pass on saying that it's like the space shuttle. Now, most people say, well, it's a battle station, and you send out a lot of TIE fighters. If you think of that way, then the closest thing you get is an aircraft carrier. And I think that's getting in the right direction, but there's a problem here, is that if you know anything about aircraft carriers, they're never by themselves. Usually aircraft carriers have supply ships, cruisers, battleships, subs that all travel with them. An aircraft carrier really is not self-sufficient. And the other thing about an aircraft carrier that I don't think is appropriate to compare to the Death Star is the power of the aircraft carrier is the fact that it can launch a lot of planes, but it doesn't have some singular weapon. And so for the Death Star, it'd be kind of like if the Death Star were just a big hangar where it just launched TIE fighters and that's all it did. Well, that's not what we think of when we think of the Death Star. Yeah, it has TIE fighters, but it can blow up a planet. And so I don't think the aircraft carrier is the best analog. And so what I've decided on is to go with the idea of the submarine, because the submarine is a self-contained vessel. It doesn't need resupply. It can stay submerged for almost 2 months on end. So it's very self-contained, kind of like the Death Star. And yes, it does have torpedoes, but its main purpose, at least ballistic submarines, is that they can launch nuclear weapons, which means they have the firepower to destroy a good portion of the planet. So here's where I think we have our best analogy for what the Death Star is like. Now, if you got a better idea of what you think the Death Star may be like, type them in the comments below. So I'm going to go with the Ohio-class submarine. Now, at this point in 2018, they are working on a Columbia-class, but this is still scheduled for production, and so the first sub won't be built until 2021, so a lot of this is really theoretical. So because of that, I'm going to back up and just work on what we know with what we have, the Ohio-class. All right, so if we're working off the idea of that the Death Star is like a sub, then the question is, how much does it weigh? Because that's our starting point. So looking at Wikipedia, if I go down here, now submarines and naval vessels, they're kind of measured in a unique way. Let me talk about displacement. And so right here, they tell us when it's surfaced, it's this many tons or long tons, or when it's submerged. Now this is more or less the weight of the water that's displaced. And according to Archimedes' principle, the water you displace is equal to the mass that you weigh, and the volume. Now we're going to get to volume, but we have to work with weight for right now. So there's our starting point, is that we can say that 1 sub equals 18,450, and the unit they used is long tons. Now, never heard of that before? Guess what? I didn't either. And so let's look up long ton. Now, long ton is a unit of mass, similar to grams. So we're going to go with the conversion, and we're going to convert that to SI to kilograms. So that means 1 Ohio class sub is this many long tons, and each long ton is 1,016.047 kilograms. All right, so now if we multiply that, 18,450 times 1016.047. Now, because the numbers are going to get really big really quick, we're just going to do this entire video in scientific notation. So 1.8746 times 10 to the 7th kilograms, and that's kilograms per sub. So that's how much one submarine weighs. Now again, we're trying to figure out how much a Death Star is going to weigh. But in order to do that, we need to remember, okay, how big is a Death Star? Well, if you remember back to episode 4, when the Millennium Falcon came out of Lightspeed into the Alderaan system, or what was left of the Alderaan system, Luke said they're heading for that small moon. And so we're going off that idea. So, whether our moon is a big moon or a small moon, we can debate that in the comments, that's fine. But we're just going to go with the moon that we have. And so, if we look at our moon, it is this size in volume. Now, what we're going to have to do, though, is what we figured out is the weight of a sub. So we need to figure out how much space this takes up, and then how many subs take up that much space. So we're going to have to do a little bit of converting, because we're going to have to convert this mass into volume. Now, because we're in metric, there's one nice thing about this when it comes to water, and we can work with that, is that 1 kilogram equals 1 liter of water. Okay. Now, a submarine has both solid space and empty space, so if you want to dispute that, go right ahead. This is an approximation, and so I invite criticism, I invite correction. We can always adjust this formula, or you can do it if you like. So that means that per sub, 1874606.7.15 liters, or 1.8746 times 10 to the 7th liters. So that's the volume of water that this thing takes up. All right. So if this is the volume of water that a sub will displace, then we need to figure out, okay, how many of that will fit into the moon of sub. All right. However, the moon was in cubic kilometers. We're in liters right now. So what we're going to have to do is we're going to have to do another conversion. 1 liter equals 0.0001 cubic meters. So that'll put us into cubic meters. So all we're doing is we're just moving the decimal over 3 places. So if we're in scientific notation, that means that it's going to be 1.8746 times 10, but now it's to the 4th. And now it's cubic meters. But we need this in cubic kilometers, not cubic meters. So 1 kilometer equals 1,000 meters, but a cubic kilometer is 1,000 cubed meters cubed. And 1,000 cubed is really 1 times 10 to the 9th meters cubed. All right. So what we have to do then is we have to take this and divide by 1 times 10 to the 9th in order to get this into cubic kilometers. So 1.8746 times 10 to the 4th divided by 1 times 10 to the 9th. Now what's nice about that is this decimal won't change. It's just going to be 1.8746 times 10, and we subtract those powers to the -5. So that's the volume of water that a Ohio-class submarine will displace. That's how much volume it takes up. So now we've got something to work with. So the volume of the sub. So now what we can do is we can say, well, what was that volume of the moon again? Let's look back at that. 21.9 billion cubic kilometers. So that's 21.9 times 10 to the 9th kilometers cubed. All right. Now it's not quite in scientific notation, but there is the volume of the moon, which we're going to use as our stand-in for our Death Star. And what we need to do is we need to say, all right, how many of these subs, which is how much space they take up, will fit into our moon. So we're going to take 21.9 times 10 to the 9th and divide by 1.8746 times 10 to the -5th. And so this 21.9 times 10 to the 9th divided by 1.8746 times 10 to the -5th. All right. So now we get 1.168 times 10 to the 15th. So this right here is the number of subs. In one Death Star. Okay. So we figured out the volume, and we figured out how many subs that is. So now the next question is, how much is it going to cost to build all of that? Another good reason why we use subs is that subs are very compact, but they are very intricate, kind of like Death Stars. They have a lot of wiring, a lot of technology running through them, and they have to be very economical about the space. So, what is the cost to build? Okay, well, if we go back to the Wikipedia page for the Ohio class, now the information's a little bit old, but it's still workable. 2.86 billion per sub. That's how much it costs to build one of them. So that means that at $2.86 billion a pop, and how many did we need? Let's write that down. We're going to have to multiply that by 1.168 times 10 to the 15th. That's a 15th subs in one Death Star. All right, now we're getting into some really big numbers here. Now so 2.86 times 10 to the 9th times 1.168 times 10 to the 15th. Okay, so what do we get? We get 3.34 times 10 to the 24th dollars to build the Death Star. All right. Now, this is not exactly dead on, but it is pretty close to what the Gizmodo article came up with. Now they just did in terms of metal and air. They said 15 septillion. Now, let's remind ourselves, what is a septillion? Septillion is 10 to the 24th. So I am within one order of magnitude. So that means within a power of 10. That means I'm close to what their approximation was, but I still disagree with that. And the reason I disagree with that is that's just assuming that you build this many subs at this price. Well, the thing is, all subs are built on Earth. The Death Star is not built on a planet. If you recall, they're built up in space. So how do we get them up here? Well, we've got to launch them all. Now, Gizmodo did go into that, but I think their numbers are a little low. Let me explain to you how I came up with my calculation. So, how do we lift stuff? Well, what I did was I went back to the best rocket that the U.S. or anyone in history has ever made. Now, at this point in time, Elon Musk's SpaceX Falcon 9 Heavy hasn't actually lifted much in the way of heavy payloads into space. So what that leaves us with is the Saturn V rocket from the Apollo era. And so, for each launch, they could lift 118,000 kilograms into low Earth orbit. Now, they could send less mass to the moon. We don't need to go to the moon. We can just get into orbit. And once we get stuff into orbit, then we can start building from there. All right. So, now we need the cost to lift it all. So, let's go back to here. So, cost to launch. Okay, so let's go back and see, all right, what is the total mass? Because all of that mass we have to split up into a bunch of different launches. Well, we have the mass of one sub. Let's see, where did I put that? All right. Nope, there, it's not there. Here it is. So 1.8746 times 10 to the 7th kilograms per sub. Now, we're not just launching one sub, we're launching a bunch. So 1.168 times 10 to the 15th subs needed. So when we multiply that, that's going to give us our total weight that we need to launch. 1.87 times 10 to the 7th. Let's be a little more accurate. 1.746 times 10 to the 7th times 1.168 times 10 to the 15th. And so we get 2.1895 times 10 to the 22 kilograms to launch. All right, so that's how much we need to launch. Now, the website that I just referenced from Wikipedia said that the Saturn V rocket can lift 118,000 kilograms per launch. All right, so when we divide that by 118, we get 1.856 times 10 to the 17th launches. That is quite a number of launches of the Saturn V rocket. Now again, if these numbers change and Falcon 9 comes online, it may be cheaper that way, but we're just working with what we have right now. So now we have to price this out. So let's go back. So researching this, cost per launch, let's go with that. About $1.16 billion. So knowing that, 1.16 times 10 to the 9th dollars per launch. Okay, so that means we have 1.856 times 10 to the 17th times 1.16 times 10 to the 9th. And so we get 2.15296 times 10 to the 26th. And so this is the cost to launch all of that material into low Earth orbit. Now, if we add in the cost to construct it, we get 3.34 times 10.4. That was our cost of building. These differ by an order of magnitude of 2. So adding in 3.34 is actually not going to change our answer all that much. The vast majority, based on my calculation, it all comes in launching, not in actually building it. All right. So it's not going to move our answer that much. 2.18636 times 10 to the 26th dollars. So this is how much it costs, based on the way I'm approaching this, to build a Death Star. Now, to make this a little more, to speak in terms of the way the Gizmodo set it up, this would be 218.636 times 10 to the 24th. I just moved the decimal point over, and 10 to the 24th is septillion. So what I'm coming up with is about 218 septillion dollars to build one Death Star. Thanks for watching. I'm welcome any comments you have. Now, some of my assumptions, they may be wrong, and that's fine. If you change the assumption, you'll probably come up with a different answer. And so, hope you had fun watching this. If you have other questions you want to see me work out, type them in the comments below.